All right, welcome back. Today I'm going to give you a brief summary and introductions to a few discrete and continuous probability distributions, mainly binomial, geometric, Poisson for discrete probability distributions, and for their continuous counterpart, we have uniform distribution, exponential, and normal distributions. All right, let's look at each one of them. Now, the first one, binomial distribution. Okay, so binomial distributions mainly refer to two particular conditions. Example is success and failure, for instance. And then you always involve a fixed number of trials. And then the event involved in this usage would be independence. All right, so all the events occur or can be modeled by binomial distributions must be independent to each other. All right. Now, binomial is a discrete probability distributions. It has the following general sort of probability, sort of properties. Sorry, not probability, but it has a general properties as listed here. Now, first of all, the general notation is written as x is having a binomial distributions with two parameters here. The first one being the n. N represent number of trials. So this n represent number of trials, whereby the p represent probability of success. Okay, and then the probability density function is given by px equal to x because this is a discrete probability distributions. So therefore, all right. So therefore, we have that probability distribution functions of or is given by here, right? Now that is the sum of the combinations of n to x. P represent probability of success. Raised to the power x here. 1 minus p represent probability of failure, where the x value range from 0, 1, 2 until n. All these are real numbers. All right, sorry, it's not real numbers. They are all integer numbers, discrete in this case. Now the mean for this uh, distribution is given as ex, and then we can sort of prove that the mean for these probability distributions can be represented by these simple calculations, number of trial multiplied by probability of success, and then its variance sigma square is given by mpq, where q is the probability of failure, or we can write down q is equal to 1 minus p in this case. Right now, how does the graph look like? Generally, it is a symmetrical graph about the mean itself, and then also about the mode, where the mode, the mean, and the medians are having the same theoretical value for binomial distribution. Right? I hope that that will give you a brief understanding of how binomial distributions work. Now, the second one being geometric distribution. Okay, now the geometric distribution is yet another example of discrete distribution. Alright, now the general properties are listed below. The notations that we use to represent geometric distributions is given as x is having a geometric distributions with a parameter p. Now the p is representing probability of a success. Now the context where we use this geometric is mainly to model an event that involve number of repeated failures before success can be achieved. Right? Okay. Now the probability mass functions to be precise. Okay, even though here I just write it down as a general notations PDF for geometric distributions. Now, because this is a discrete probability distributions, the term that I should be using should be okay. Hold on, just let me show it to you. Instead of calling this as a PDF, it should be called PMF there. So that is probability mass function. It's just the discrete counterpart of probability density function. So for this geometric distribution, it has probability density, probability mass functions given as 1 minus p raised to the power x minus 1, where the x range from 1 to infinity, and then x represent number of times certain event fail before success can be achieved. So 1 minus p represent the probability of failure in this case. Now the mean for this distribution is given by 1 over probability of success, whereby the variance is given by 1 minus p divided by p squared here. Now the graph is no longer symmetrical. If you look at the outline, it's more like positively skewed because the tail is on the right hand side here, right? Now I hope that will give you a brief understanding of how geometric distributions look like. Okay, now next we have another example of, okay, hold on, just let me clean this up first. Okay, so next we have Poisson distribution. This is yet another discrete distribution. Now the general properties are as follow. We can write its general notation as such. X is having a Poisson distributions with a parameter lambda. You can see that from here. This is the parameter here. All right. Okay. Now, briefly, this lambda represent the average mean, average number of times over a certain interval, right? So just to give you a general idea of what this lambda represent, it actually represent in general the average numbers of times certain event occur over a certain period. It can be over certain periods of time. It can be over certain periods of duration, for instance. Now, the probability mass function is given by such, right, whereby the lambda is a constant parameter. The x range from 0 until infinity, whereby all these x are all discrete values. They are all integer number. The mean for Poisson is given by lambda, whereby the variance is given by lambda also. Now the proof to all these mean and variance will be provided in another extra videos. So if you are interested to apply some of your pure mathematics in proving the mean and variance, you can check out the next videos on this, right? Okay, I hope that is clear. Now the graph for Poisson looks something like this. Um, it's a skewed graph. It's no longer symmetrical as compared to binomial distribution, right? Okay, now that is our Poisson distribution. Now next we're going to move on to continuous distribution. For continuous distributions, we have the first one, uniform distribution. So we know that this is continuous probability distributions. The general properties are here. Now, because this is a continuous probability distribution, so we'll be using the term probability density function. So it has a probability density functions given as such, 1 over b minus a, whereby the domain for this function is a and b. Otherwise, it will be a 0. Now, by using a pure mathematics proof and some algebraic manipulations, we should be able to prove that the mean is given as such, whereby the variance is given as this expression here. Now, the graph for uniform looks something like this. So you can see that based on the definitions for the uniform distribution, this function only exists between these two intervals a and b. All right. So I hope that is clear. That's the first continuous probability distribution. Next, we have exponential distribution. Yet this is another continuous probability distributions. All right. Now these exponential distributions uh, look quite similar to its discrete counterpart, geometric distribution. It's just that exponential distributions are mainly used to model event that involve a continuous quantity, such as um, durations of times before certain machine would fail to work, for instance, right? Instead of having uh, discrete numbers of time that certain event fail before success has been achieved, right? So exponential distributions looks quite similar to geometric distribution. It's just that exponential is used to represent continuous quantity, whereby geometric distribution is used to represent discrete quantity. Right. Now the general properties, as usual, the general notation is written as x is having an exponential distributions with parameter lambda. Now its probability density function is given by such where the lambda must be greater than 0. Now by using algebraic manipulations, we should be able to prove the exponential um, x, sorry, not exponential x, sorry, is the mean for this exponential distribution as 1 over lambda, and then the variance is given by 1 over lambda square here. Right. All right. Now the graph itself, in general, the graph looks something like this. Okay, let's see. All right, so it's also positively skewed because the tail is on the right hand side, right? Okay, so I hope you get a general understanding of how exponential distributions work. Okay, now lastly, we're going to look at the last and um, most popular continuous probability distribution, which is known as normal distributions. I think most of you have seen the bell-shaped curve. This is a symmetrical distributions centered at a 0 here based on this graph. Right. Now it is a continuous distribution. Um, it has a general property as listed below. So here we say that x is normally distributed with the mean given as such. So the mean is here. So this is the mean. And then this part here will be the variance itself. Okay, right. And then the probability density function is given by this very complicated formula here. But anyway, the x are all real number. So you can see that from this graph itself, the mean is quite direct. You can see that from here, the variance is given by lambda square. All right, now that will give you a general idea of how all different types of discrete and continuous probability functions look like, and then what are their general properties are, which you might need to use it for chi-square um, analysis, right? So thank you very much for watching this. Okay, I hope this has been a useful learning informations for you, right? Until I see you guys again, all right, take care everyone.